any. Now we can finally discuss the proof of the unitarity of the S matrix, at least in the simplest case, at lowest order perturbation theory, which however is already a very interesting and non-trivial case where several interesting things go on. Just to repeat, unitarity means that probability is conserved. The sum of all probabilities must add up to 1 in a quantum theory. And it leads to a corollary, namely the optical theorem, which is the thing that we will check, namely the square or the total probability of a fixed initial state into any final state is related to the imaginary part of the forward scattering amplitude of the same initial state. And the interpretation that is useful for us today is that lower orders actually fix uniquely the imaginary part of higher order loop diagrams in order for unitarity to be valid. And the question that we have is, we know it's true if we sum here over all final states including the unphysical ones, and the question is, does it remain true even if we only sum over the physical final states, which we actually want to consider as with physical interpretation in our theory. Okay? And so that is what we want to check. And so let's do it. Oh, again, an interesting new kind of chalk. I think that seems okay. Oh, good. So let us look at the simplest example, and let us specifically choose QCD here for our example with quarks and gluons and for DF Popov ghosts. And then in QCD we fix an initial state which is a quark anti-quark state. So I use QCD notation here. Q stands for quark field, which is a fermion field. And we have a 2-particle initial state. And then, since it's the simplest case, we look at lowest order 3-level Feynman diagrams. For 3-level Feynman diagrams, for us, the only interesting final states that we need to sum over also involve 2 particles and not infinitely many particles. So the final states we have to consider are all possible 2-particle states which can appear in a scattering of QQ bar. That would be QQ bar also in the final state, but it could also be gluon-gluon in the final state. I call it AA. But it could also be ghost-anti-ghost in the final state. All of those final states conserve charge and everything else that needs to be conserved. Yes? Yeah, but now we have to sum over final states which are even unphysical. And we have discussed the Hilbert space, or first of all the Fock space of our theory without interactions, and there the ghosts appear as 1-particle states. And so that is the point. On that space where the ghosts appear as states in this indefinite norm space, on this space we know the S matrix is unitary. And so we will soon write down the equivalent of this relation, but specifically for this case here, and then you will see exactly how the ghosts appear. But that statement you are referring to, that the ghosts only appear in internal loop diagrams, applies for physical matrix elements. if we really want to calculate ultimately a physical observable, then that is true. And that is exactly the point. And then we want to know whether for those physical matrix elements unitarity holds or not. And so far we don't know it. But that's exactly the point. So let us consider this case and check the optical theorem relation at the following order in perturbation theory. Namely, let us check it at the order g to the 4th power. You know, we are doing perturbation theory, so Feynman diagrams are expressions in some order in the coupling constants, and we can now check this equality here at any order that we want. We want to check it at this particular order, which is already 4th order in the coupling. All right, therefore, as I said, let us write down the equation that we need to check for that specific case. That will be a table. So I write down on the left hand side the diagrams for TFI, and the left hand side then contains TFI square. Therefore, what is the order of TFI we need? We only need 2nd order in the couplings. So we need to write all possible TFI Feynman diagrams at this order. And on the other side of the equation, we need the imaginary part of the forward scattering amplitude, TII, at the order g to the 4th. So that will be a table. Let us fill the table, and let's keep in mind that general outline over there. And so what are the Feynman diagrams for TFI? And they can be grouped according to the final states. So let's first consider the Feynman diagrams giving TFI for the final state QQ bar. What does it mean? It means we need the scattering matrix element for the process QQ bar goes to QQ bar. So at 2nd order in the coupling. Who knows what I'm talking about? Which Feynman diagram? How could the Feynman diagram look like? Which does that? QQ bar to QQ bar at order g square? Yep, right, okay. This very simple Feynman diagram. Okay. And let's draw the arrows here. So this Feynman diagram, is this the only Feynman diagram? You mean like this, a 2nd particle here? Ah, okay, but we are only looking at QCD. Then there is no photon. But there is nevertheless a 2nd diagram just for QCD. That is a gluon now. But there is a 2nd diagram with a gluon exchange, which would be T-channel. Right? So like this. Okay, let's draw also the arrows. So then you see that it works. So here the arrows indicate a particle or antiparticle, quark, antiquark. Here quark, antiquark like this combines to a gluon, and here incoming quark, outgoing quark, or incoming antiquark, outgoing antiquark. All the vertices work in this way. Anything else? No. This is the total complete list of all Feynman diagrams at this order for this process. And so if we calculate those diagrams, we have an exact expression for TFI for this particular final state at the order we want. Okay? So that would be totally explicit. Now let us immediately write down some Feynman diagrams for TII. What is TII? TII is a scattering for an initial state into the same state. So okay, that is the same, but we need now quark quark, quark antiquark going into quark antiquark, but at the order g to the 4th. What is an order 3 to the 4th Feynman diagram for quark-antiquark going into quark-antiquark? Yes, let me draw also some arrows. Anything else? Yep. This sort of thing. Okay. Let's not forget about this, but let's draw it later. Let's not forget about it. But there is another Feynman diagram which I want to draw now. For example, this one. So, and so on. There are a few more Feynman diagrams. So we need the imaginary part of the Feynman diagrams. First of all, to spell it out, these are diagrams of the right kind. I goes to I, Q bar goes to Q bar at 4th order in the coupling. Now let me invent a notation for extracting the imaginary part. A common notation for extracting the imaginary part is simply to cut the line, cut the Feynman graph. So now I will use red color, but whatever. So I symbolize it here. So I cut the loop with this red color here, and also I cut this loop here with a red color, and that simply denotes that I extract only the imaginary part of the loop. What do you see if you now really think of this diagram as one half diagram left of the red cut and another half to the right of the red cut, and what happens here to the left of the cut and to the right of the cut? What do you discover? Exactly. Yep. Yeah, right. Can you do more? For example, I combined here this with itself, gives that. I combine this with that to obtain this one. Could we do more? So, for example, like this. I had the impression you were describing a different box diagram, but if you were describing that box diagram and we also symbolize the imaginary part by such a cut, then you discover now that here we have exactly this diagram twice. And so on. Clearly you can now combine these diagrams in all possible ways. There would be exactly 4 ways to combine them in such a way, and each time you will get a valid one loop diagram which gives rise to QQ bar to QQ bar at the order 3 to the 4th. So plus dot dot dot, there is one additional diagram of this kind. Let us go on. So here on the left we are done with the final state QQ bar, but we also need to consider all the other final states. Let's consider AA, gluon in the final state. So then there would be a few diagrams, for example this diagram here with a triple gluon vertex, and then such diagrams which look like this with such a T-channel exchange. And there are a few more. For example, there is also this one with the 2 lines exchanged. And you could write these diagrams twice, and let me do it. You can write them for transverse gluons in the final state, and you can also write them for unphysical gluons in the final state, because we can distinguish in the way we did it in the morning. So then the diagrams look the same, but the epsilon polarization vectors that we would use to calculate the TFI would be different. Here we use only transverse epsilon polarization vectors. Here we use the other ones. Then we can distinguish between the physical and unphysical final states. Okay, let us do the loop diagrams. QQ bar goes to QQ bar at order G to the fourth. Now we can do something similar. Let me write down a first example. So here we have a Feynman diagram at the right order for the right process, and we need the imaginary part symbolized like this, and you see it corresponds exactly to this diagram squared. So once in this order and once in the opposite order corresponding to complex conjugation. Something else, for example, this diagram times the other one would give maybe something like that. This Feynman diagram. And so on. For example, if we combine this one with itself, we get the other box diagram. This is the box diagram from Paul, I think. Can we?
أولا أنا داير يعني أذكركم بما كتبته في كتابي الفائد وهذا 54 و 55 بأنه كلما تعمقت التفاعلات كلما ناقصت المسافة X في التفاعلات كلما زادت تعقيد التفاعلات خرج جسيمات أكثر. وهذه واضح الآن بما يقوله هو في QCD. ينظر لهذا العدد الضخم من الدياجرامز، دياجرام خاص بالكوارك، دياجرام خاص بالجلوز، سنرى تاني ماذا يحدث. هذه بسبب المسافات الصغيرة. يعني احنا نتكلم عن التفاعلات في QCD طاقات عالية مسافات أقل تعطينا مجموعة من الجسيمات، مجموعة من الفايمان دياجرامز. هذا أنا مقصوده في كتبي. وتتناسب هذه المنتجات البرودكتس تتناسب مع الطاقة، والطاقة تتناسب مع زيادة الطاقة تتناسب مع تقليل المسافة. وربما سيظهر شيئا في هذه المحاضرة تعبر عن السيمتري بريكين، اللي هو نجد أن هناك جسيمات أكبر من الأخرى، من الجسيمات المنتجة ذاتها نجد جسيمات أكبر من الأخرى. يعني مثلا نجد الكوارك، التوب كوارك مع مثلا مع البوتوم كوارك 172 173 جيجا مع 4 جيجا. نجد أيضا الجيل الثاني البوتوم مع السترينج أو الشار مع السترينج 1 جيجا 1.2 جيجا ميجا إلكترون فولت، والسترينج 102 ميجا إلكترون فولت، وهكذا. الأب مع الداون يعتبر تفاعل ليس عميقا جدا، بالرغم انه هو QCD كلها تفاعلات عميقة لأنه كتلتهم متقاربة. الأب والداون 2 أو 3.5 و 4.8، فكتلتهم متقاربة. لهذا يكون أقل التفاعلات عمقا. بعد ذلك الجيل الثالث تفاعلات تكون عميقة. نفس الأمر يتفق مع الليبتونات. ربما سيذكر هذا النوع من الكلام، سيذكر إذا كانت معادلة تكمل دقيقة ستخبرنا هذه الأمر بوضوح، بالإضافة إلى تنوع التفاعلات. طيب تعالوا نواصل.
Also combine those with those diagrams in such a way. That makes no sense because the final states are different. So if we flip them around, then you cannot connect such a diagram to this one. And so there is no counterpart for such a combination here on the right. Can I also write those diagrams here twice, once for physical and once for unphysical gluons? No, I cannot, because in the loop, the propagator is just a propagator Feynman rule. We cannot, okay, we might, but we do not usually split the propagator into different components corresponding to physical or unphysical gluons. So there is just one gluon propagator with a certain Feynman rule, and then there is one diagram. And the gluon propagator comes from gauge fixing in the Lagrangian. It necessarily contains unphysical degrees of freedom, and it also necessarily contains dependence on psi, the gauge parameter. And so this diagram contains physical and unphysical information, and it corresponds to both here. Finally, maybe let me write this down. The propagator depends on psi, also unphysical degrees of freedom. But now finally our last final state, ghost anti-ghost. So we now need Feynman diagrams at order g square, and now comes the answer to your question, at least explicitly. Feynman diagrams with ghosts as external fields. Here, there is such a Feynman diagram. This is the only Feynman diagram which exists at this order. And now we want here all the loop diagrams. So here there is such a loop diagram. With a Faddeev-Popov ghost loop in the gluon propagator. And again you see the same correspondence to the diagram on the left. This finishes our table. This is the complete table. And to repeat, on the right we have simply written down all one loop diagrams at the order g to the fourth, which correspond to QQ bar to QQ bar. And there are, just to repeat, in the normal language there is gluon self-energy diagrams with quark loop, gluon self-energy with gluon loop, gluon self-energy with ghost loop. There are vertex correction diagrams with this QED-like vertex correction diagrams with a non-abelian vertex, and there are two kinds of box diagrams. So we have the complete set of all one-loop diagrams. We need the imaginary parts, and the extraction of the imaginary part already illustrates that there is a relationship between the loops and the tree-level diagrams of those processes here, because each loop diagram can be visualized as a combination of two such diagrams here. And that is no accident, but this is exactly the graphical illustration of the optical theorem. That is the optical theorem which tells us that exactly the sum of all those imaginary parts is the same as the sum of the squares of these diagrams. That is what the optical theorem tells us. Let's write down exactly some equations about the optical theorem. I will write down various shapes and forms of it to illustrate it, I hope, as well as possible. So the first relation is the following, which is directly a copy of the general statement, namely a sum of all final states, let's leave some space here, of TFI square is equal to 2 times the imaginary part of TII. So that is the general relationship now concretely applied to order G to the 4th and for our concrete initial state QQ bar. And then in our sum here we only get a contribution of those final states that we have discussed, namely QQ bar, comma AA, comma CC bar. And then, because our vector space of quantum states has indefinite norm, sometimes we need a plus minus prefactor in front of the TFI square. Namely, for the negative norm states, we need to have a minus. For the positive norm states, we need to have a plus in order for the unitarity relation to be fulfilled. So, but with this, we have a full relationship which we know holds. So this holds by construction. You can also check it explicitly by calculating everything, but it is no question that it holds by construction of the S operator as a unitary operator on this general space of states. And so that corresponds to S deca S on the full theory, including unphysical states, is 1. Let's call this equation star. So that is our basis equation which we know to hold. And why does it hold? Technically you can understand how it can hold by this visualization that I gave you here. So clearly the imaginary part of this diagram has something to do with a square or with a combination of this 3-level diagram times the other 3-level diagram. The imaginary part of this diagram has something to do with a combination of this 3-level times that 3-level diagram, and so on. And because of this diagrammatic correspondence between the imaginary parts and those 3-level diagrams, this is immediately valid. Now let us step by step go to the question that we really want to answer, namely, does the optical theorem also hold when we only sum over the physical states? But before we go to the ultimate final answer, let us do some intermediate discussion, which is of historical interest, namely, which goes back to the discovery of this whole approach, namely, who discovered the ghosts? No, the ghosts were discovered earlier by Feynman. And let us investigate how somebody like Feynman could discover the necessity for ghosts. Namely in this way. So first of all, a secondary statement, which is just an intermediate statement. You can do the analysis in this graphical form. There is a one-to-one correspondence between the imaginary parts of those loops and those 3-level diagrams to the left and to the right of the red cut. And that in particular means that there is also such a correspondence for the last line for the ghost. So the imaginary part just from the ghost loop is the same as the square of this Feynman diagram with a ghost in the final state. And let us just write this down. You can check this, for example, by temporarily doing a trick. If you want an explicit proof, temporarily use an arbitrary value of this vertex. Okay, if you use an arbitrary value of this vertex, then you can ask, is the optical theorem fulfilled for any value of this vertex? And the answer is yes, because for any value the Lagrangian is Hermitian, then the construction of the S operator gives something unitary for any value of that coupling. Therefore the relationship must be fulfilled just for diagrams involving that particular coupling alone, and these are only these diagrams in the last line. Therefore the relationship that we wrote down is valid just for the last line alone. So let's write this. Then we have the following: sum over all the ghost anti-ghost final states. They have negative norms, so with minus TFI square is equal to 2 times the imaginary part of TII, but now we have only the ghost loop. Okay, so this relation is also valid. Now we can go back to Feynman's time and forget the ghosts. It's a little bit unfair to say Feynman forgot the ghosts, but they just were not discovered at the time. So nobody knew there would be something like ghosts. That was in the 1960s. And if you do not know about ghosts, then you would write down the following formula. Namely, your unitarity relation would be the following. In the left, you have the sum over all final states with QQ bar, physical gauge bosons, and unphysical gauge bosons, plus minus 1 times TFI square is equal to 2 times the imaginary part of TII, and here you have no ghost loop. Okay. You do not have ghosts, therefore you calculate your TII without the ghost loop. Then you get all the diagrams except for the last one. And on the left, you have all the states, including unphysical ones, again without the ghosts. So, and this is also valid. This is also a valid equation. And so you see all these equations that we wrote down are valid. And so the first one is the ultimate one. This is a simplified version, and if we subtract this from the first one, we get that one. So they are all valid. Now the question is, do we have a unitary physical S matrix? And in order to have a unitary physical S matrix, we need to ask whether the equation remains true if we only sum over the physical final states. So this equation is true. Now that equation without the unphysical final states, does it remain true, yes or no? The answer depends on whether the contribution of the unphysical states is 0 or not. Is it 0? That simply means, is the square of these diagrams 0? The answer is no. The square of these diagrams is not 0. And therefore, these unphysical states contribute the contribution is non-zero, and therefore the equation becomes incorrect if we leave out the unphysical states. So if AA unphysical is dropped, equation becomes wrong. And that was Feynman's discovery. And of course, he knew what it meant. It meant something very deep. Let's write down the deep consequence. The physical S matrix without ghost loops violates unitarity. So the equation without ghost loops violates unitarity, and we can say it in a simple way: the imaginary part is wrong. As we said, the imaginary part of the higher orders is predicted by the lower orders, and the equation is wrong. That just means the imaginary part is incorrect. It violates the relationship that it should fulfill coming from unitarity. Wrong imaginary part of the loops. So, and then what was Feynman's discovery? Feynman, clever as he was and not caring maybe so much about formalism, he simply said, okay, if we invent new particles which only appear in loops, and we write down such a loop diagram with very specifically chosen Feynman rules for these couplings, then that loop contributes an imaginary part which corrects for the equation. And that was the discovery of ghosts.
طبعا كما ذكرت أهمية الجوست في الفيديو السابق هو أنه يعبر عن combinations بين الآن physical اللي هو تحديدا ال L وال S، والتي تعطينا طاقات عالية، والتي تعطينا النيجاتيف نورم بسبب أن التفاعل يكون تفاعل شبيه بالثقب الأسود، الأبعاد تنقلب فيه، وهذا يظهر في QCD وعند الطاقات العالية. فالجوس هي طاقات عالية ومكثفة جدا، وهي المسؤولة من أنها تعطينا مركبات كثيرة وفيها أنسيمتري كثير، يعني تعطينا جسيمات كثيرة ولكنها السيمتري داخلها مكسور. ربما يتوصل الأستاذ المحاضر لهذا الأمر أن السيمتري يكون مكسور كثير بداخل الجسيمات التي تخرج من عند الطاقات العالية التي تكونها الجوست، وربما تكون هذه الماس جاب. يعني إن شاء الله يطلع كلامي صحيح، لأنه لو طلع كلامي صحيح هذا يعني أنني بصدد كتابة ورقة علمية أخرى عن الجوست بارتيكل أو الجوست بوزونز. طيب نعيد المرة أخرى أنه الجوست أهميتها أنها طاقات عالية، لأن هي عبارة عن combinations وعن physical states مثل تكاثف بوز-اينشتاين، فتعطي طاقات عالية لفضاء صناعي الأبعاد، ويقوم بكسر هذه الطاقة العالية ويعطي كمية أكبر من الجسيمات. وفي هذه الجسيمات فرميون تكون السيمتري بينها مكسورا، بحيث أنه تعطينا السير على ما أعتقد السكند جنريشن والثيرد جنريشن وربما أكثر من ذلك. سنتأكد من هذه الأمر، لكن ما أريد أن أقوله أنه الجوست هي حقيقية وأنها تعبر عن نوع من الجسيمات ذات طاقة عالية جدا تتكون من داخل اللوب كما ذكروا، لا تخرج خارجا لأن هي انفيزيكال. وربما الدبليو زي تكون أحد هذه الجوست، برغم أن الدبليو زي استخدم الكيو اي دي، لكن عند التفاعلات العميقة تكون أحد هذه الجوست، ربما تكون ذلك. وفي التفاعلات في الكيو سي دي سنرى هو الجلون نعم الجلون انتراكشنز ربما يكون أحد هذه الجوست، خصوصا 4 جلونز 3 جلونز 4 جلونز يكون أحد هذه الجوست. تعال نتأكد من هذا.
So on this level, one would say the ghosts must appear in the loop Feynman diagrams in order to correct the imaginary part which we need to obtain from the physical unitarity of the physical S matrix. So now we understand also this point, and then we can finally write down the actual equation that holds in our theory where the ghosts exist. And so let's do this with ghosts. Let's look at only the purely unphysical part of the equation. So if we write only the purely unphysical part of the equation, then on the left-hand side we have a sum over the unphysical polarizations of the gluons and ghost anti-ghost final state plus minus 1 times TFI square. That turns out to be 0. This sum is 0. This holds because of a certain Slavnov-Taylor identity. C exercise. And also later in the lecture we will discuss the Slavnov-Taylor identity in more generality than on the exercise sheet, but on the exercise sheet there is an exercise number 2 which contains exactly the proof of this statement. Yes. The CC bar final state has also negative norm as we discussed in the morning, and so for that also the -1 is needed. And for the gluons, for this A0 polarization, which also has negative norm, it is also needed. No, the A3, for example, lambda equals 3 polarization has positive norm, is also unphysical. And also there two particle states might again have different norms. So for example, a one particle state with one lambda equals 0 has negative norm. Maybe then a two particle state with lambda equals 0 twice might have positive norm again. I didn't actually think about that, but probably it has -1 squared as the norm, which is +1. So, but in the exercise you will first of all derive the corresponding Slavnov-Taylor identity by explicitly evaluating the corresponding Feynman diagrams, and you will also have an explicit formula for the +-1 here, which then looks a little bit more explicit, coming from the epsilons, these polarization vectors for the polarizations of the gluon. So, as we said, all the previous equations, we know they are true by construction simply from the hermiticity of the Lagrangian. This equation is very different. It is extremely non-trivial from that point of view. It doesn't hold by the simple argument. It holds because of a Slavnov-Taylor identity, which is a detailed property of certain Feynman diagrams, which is not obvious at this point, but therefore it's delegated to the exercises. So But now, if we use this equation, which will be proved in the exercise, then we can plug in this into the equation at the top, and then the unphysical stuff cancels among itself on the left-hand side of the equation. And what remains on the left-hand side of the equation is just the sum over physical final states, and the right-hand side is unchanged. And that is the final result. So hence, let's say this is 2 star. If we combine 1 star plus 2 star relationship, then we obtain the following, which is the final statement, namely the sum over only physical final states, F equal QQ bar, and physical AA. And here also they always have positive norm, plus TFI square is equal to 2 times the imaginary part of TII, where here we have the full TII with ghost loops, of course. Because the ghost loops were also included at the top. And that is the final relation of this section. That was to be established. This corresponds to the physical unitarity of the physical S matrix. So this is valid in our setup of the BRST formulation of the Young-Mills theory. And to interpret it once again, on the left-hand side, we have a sum of physical scattering matrix elements of a physical initial state into all possible physical final states. We square them, and that would be the left-hand side of the optical theorem for the physical S matrix. On the right-hand side, we have the forward scattering amplitude and take the imaginary part as prescribed by the optical theorem. And that imaginary part is calculated with the Feynman rules of our theory. The Feynman rules of our theory contain ghosts, and therefore the Feynman rules contain, by necessity, this ghost loop. And so what it tells us is that the Feynman rules that we have formulated give automatically the correct imaginary part, which corresponds to a physical unitary S matrix. That is the point. So we can compare it to Feynman's formula. So if Feynman leaves out the unphysical stuff and only sums over physical initial states, then this left-hand side of the equation for Feynman is the same as for us. He has the same 3-level diagrams without ghosts, only physical states in the initial state. We calculate 3 levels, square them, and get a left-hand side, the same as for us. But his right-hand side is wrong because he didn't have the ghosts. We have the ghosts, and therefore our imaginary part is correct. And so we can interpret this by saying that the ghosts are necessary to correct the imaginary part of the loop diagrams such that the imaginary part matches to the left-hand side of the optical theorem just coming from physical states. That is the outcome of the introduction of ghosts. Any questions? This is one of the most important fundamental properties of quantized Young-Mills theories, which is necessary to establish that these theories make sense in the first place, that you are allowed to talk about them as physical theories, that they can be interpreted in the usual sense of quantum mechanical theories, with probabilities, probability amplitudes, and so on. We have established that we can define a physical Hilbert space, which has a complicated definition with equivalence classes, but ultimately it is defined, it has only positive norm states, and on this positive definite Hilbert space we have now a unitary physical S matrix. And so that gives us confidence that these quantized gauge theories make sense and can be interpreted. So similarly, in the morning we have discussed the other problems and magical solutions. So to summarize them, there was Lorentz invariance is at stake because the epsilon polarization vectors are not 4 vectors. gauge dependence could play a role because the psi parameter exists in Feynman diagrams, and all of those problems are solved by a specific what or Slavnov-Taylor identities, and here there is again a Slavnov-Taylor identity ruling the unitarity of the physical S matrix. That ends our discussion of quantized Young-Mills theories with tree-level discussions, and for the remainder of this section on Young-Mills, we will look at higher orders. So we will study the renormalization of Young-Mills theories, and in order to do that we need to take an even more serious and general look at Slavnov-Taylor identities. And by doing this discussion of Slavnov-Taylor identities in more detail, we will also rediscover those identities like this one here in a more general form. So far you will prove this in the exercise by explicitly writing down Feynman diagrams. Also the other identities we needed in the morning, we know they are true by explicitly looking at the Feynman diagrams. But now we will look at higher orders. We will study Slavnov-Taylor identities in general, and then you will see that from the general formalism, those very same identities drop out, or let us say, come out once again. But then they are immediately valid not only at tree level, but at all orders. And then you see that this would be the basis of general proofs of all those properties which are valid at all orders. We will here not spell out all the proofs of everything in all detail, but we will sketch the logic of all the necessary proofs. And the basic common tool for all of them are the Slavnov-Taylor identities, so we will look at them. But we will sketch how they play a role in all the different aspects of the proofs. But and so one could do that already without renormalization, but we will do it in combination with discussing renormalization, because that is obviously also important. So let me clean the blackboard and then we can do that. So let us discuss renormalization and Slavnov-Taylor identities in a combined way. As I said, one could do it also one after the other, but we will do it in combination. Let me write down some questions. First of all, as you know, once you start calculating the loop diagrams, there are divergences. Ultraviolet divergences coming from the integral, which diverge at large integration momentum. So the obvious question is, can all these ultraviolet divergences be cancelled? And the next question is, in QED we had put forward a scheme which is very common and well known, so-called renormalization transformations. And so the secondary question is, can the divergences be cancelled by a usual renormalization transformation of fields and parameters? So that would be very nice if that were true, and I will tell you exactly what we mean by this renormalization transformation. And the answer is yes, of course. The answer is yes. The divergences can be cancelled by this multiplicative or by the so-called renormalization transformation of fields and parameters, which is a very non-trivial but important statement. for the treatment of higher orders in these Young-Mills theories. But that is the first question. But it is not the only question. The second question is what we have discussed in the past hours, namely, is the resulting finite theory actually sensible? Is it a correct theory which can be interpreted in a usual physically meaningful way? That means, so whether these statements that we have discussed in the past hours valid at all orders. So do we have Lorentz invariance in all scattering amplitudes? Does the gauge fixing parameter drop out of physical scattering amplitudes? Is the physical S matrix unitary at all orders? So this is a highly non-trivial question, and as you can guess, its answer will depend on certain Slavnov-Taylor identities, but also this question can be answered by using certain Slavnov-Taylor identities, and that is why we need to discuss renormalization, the physical interpretation, and Slavnov-Taylor identities all in a combined way. Let me write down the basic statement of this section. The basic statement of this section is the answer to both questions is yes. So that gives basically the main message. You can forget about everything else, but that tells us that Young-Mills theories make sense. Okay, and the central tool is the Slavnov-Taylor identity, which is the reflection of BRST invariance on the level of green functions. So in this way, we have a clear plan for the next lectures. We will at least sketch the proofs and introduce all the necessary ingredients. But we will make a few simplifying assumptions. Namely, we consider here a theory like QCD, which is a gauge theory, maybe Young-Mills theory, non-abelian gauge theory with a simple gauge group, where we have only one single gauge coupling. And we assume, like it is the case in QCD or QED, that there is no gamma 5 in the theory. So if there are fermions, there are also nice theories which do not even contain fermions but only scalar fields and vector fields, or only vector fields. But if we have fermions, let's assume that there are no interactions involving gamma 5. Then we are working in perturbation theory. So no non-perturbative statements, and we use dimensional regularization. To have a concrete way to deal with the divergent integrals. Okay, that is our starting point, and in this context, which is a very wide context, actually, let's proceed. So first, let me introduce this notion of renormalization transformation so that we know what we mean by this. So this is not yet a theorem, it is just a prescription to do something, and then we will study afterwards what that gives us. We start with a classical Lagrangian. I now call our Lagrangian classical, with CL stands for classical, which is the Lagrangian which we have in our tree-level theory, or the quantization of the free theory as well. So which is the one that we looked at so far? It contains the gauge invariant part with the F-mu term, also possible interactions for quarks or other matter fields with covariant derivatives. And it contains from BRS the gauge fixing and Faddeev-Popov-Ghost terms. This Lagrangian here, as you remember, hopefully was defined as a total BRS variation of something else. Therefore, it's by construction itself BRS invariant, and it contains then two terms. One is the gauge fixing term, the other one contains Faddeev-Popov-Ghosts, and the two are related. And the relationship between the two corresponds to the BRS invariance of this whole thing. Now, once we have defined this Lagrangian, it is at first, of course, defined in four-dimensional space-time, but now we do dimensional regularization, so we go to d dimensions. And then we need to ask, what does this Lagrangian mean in d dimensions? And the answer is trivial, because all the quantities in this Lagrangian have an obvious d-dimensional counterpart. They can, without any difficulties, interpreted immediately as d-dimensional quantities. Like all A mu's are now d-dimensional vector fields, all d mu's are d-dimensional derivatives, and so on. Gamma mu as well. So let us now interpret all quantities in d dimensions. And then we have already our regularized theory. And that would be different if we had gamma 5 in our theory. Okay, then we have the following recipe. The recipe is what we call renormalization transformation. Is the following replacement rule. It's a replacement rule. All quantities which appear in the Lagrangian, fields and parameters, are now replaced by new quantities, by so-called bare quantities and renormalization constants. So let's simply write it down. One parameter is the gauge coupling, G. That is replaced by a bare gauge coupling, which we call G bare. And this can in turn be written as ZG times G. So we write the bare gauge coupling as the original gauge coupling times a so-called renormalization constant, which we call ZG. Similarly, we do it for all the fields in the theory, and which fields are there. So let's use QCD language. Then we have a quark field. But this is replaced by a bare quark field, which can be written, or is written by definition, as square root of ZG Q times the original quark field. So this is ZQ, the field renormalization constant for the quark field, and we write by convention square root of ZQ times Q. Then what else do we have? We have the gluon field, A mu, is replaced by a bare gluon field, A mu, bare, which we write as square root of ZA times A mu. So there is a field renormalization constant ZA for the gluon field. What else do we have? Any other ideas? which other quantities appear in the Lagrangian. The ghosts and anti-ghosts, which are treated differently. Let's begin with a ghost. Let's say, let's leave here a blank line. CA goes to CA comma bear, which we write as square root of Z. Okay, that is a small blank line. Square root of ZC times CA. Then what else do we have? There are the anti-ghosts, something else. Which mass? Ah, the quark mass. Okay, let's not use a quark mass. Massless QCD. For simplicity. But otherwise you were right. So we would write here a mass. M goes to M bear is equal to Zm times n. Very, very possible. But just additional work to write. So let's drop it. It doesn't change the big picture. Anything else? Yep. Yep. The B field. The B field. So let's write here the B field. BA. Anything else? We already mentioned the anti-ghost. So let's also write down the anti-ghost here. Why do I write them together? Because they are the BRST transformations of each other. So they should renormalize in the same way. That makes it simpler. Something else, also the gauge fixing parameter psi appears in connection with the B field and also the anti-ghost, all in the gauge fixing part of the Lagrangian, and they all renormalize in a dependent way. So in principle one could introduce some independent constants for all of them, like we did for the rest, and then we would discover that all of that would be unnecessary. So let me immediately tell you the conclusion. They can all renormalize in a dependent way, namely depending on the gluon renormalization. And the basic idea is that the gauge fixing term itself does not renormalize. And the reason is that the gauge fixing term is bilinear in the fields. Bilinear in the fields. Bilinear in the fields means it is a free theory with no interactions. And therefore, since there are no interactions, there are no higher order corrections. Therefore, the gauge fixing term does not need to be renormalized. And so that is the intuitive idea. So let's therefore write down such renormalizations that in the gauge fixing term just everything cancels between each other. So for example, the gauge fixing term just here maybe contains psi over 2 times b square. It also contains b times d mu a mu. These are the two terms it contains. And so we say this is a free theory. B is free, B doesn't interact, therefore there are no corrections to any of those terms. A renormalizes into square root ZA times itself, therefore B must renormalize with the inverse, if my intuition is correct. So 1 over square root of ZA times BA. Then this term overall does not change under this transformation. Similarly, psi times b square should also not change. B transforms like 1 over square root ZA, therefore psi should renormalize. And first of all, C bar is like B, and psi goes to ZA times psi. Then psi times b square also stays invariant under this renormalization transformation. So I gave you an intuitive explanation that this is a free Lagrangian with no interactions, therefore there is no change under renormalization. You might not believe me, and it's certainly not completely obvious for you, but this is the intuitive explanation, and it motivates you why I have here something special. And anyway, we need to check, that is part of our main statement, that this renormalization transformation is all we need in order to cancel all divergences. And so since the big statement is anyway totally unobvious, there is no point in not making here some small side comment to the big statement. Okay, so that is our renormalization transformation, and under this renormalization transformation, the Lagrangian L classical becomes a new Lagrangian which we call L bare, and we immediately then split the L bare into the original L classical Lagrangian plus a so-called counter term Lagrangian. So CL plus L CT, CT stands for counter term. And by plugging in those relationships here, you see that the bare Lagrangian contains the original fields and the original terms all multiplied with certain combinations of Z factors. And so you can always extract the original term plus some remainder, and the remainder depends on Z factors minus 1, something like that. So maybe let me add here one line. If you write all these Zi as 1 plus delta Zi, then this counter term depends on all these delta Zi. So this is the renormalization transformation, and now by this renormalization transformation we change our Lagrangian. We change our Lagrangian to a term which is the original one plus something new, which has a similar structure but contains all the delta Z factors. And we can adjust the delta Z factors such that the divergences are cancelled. That is the idea. And now the point is, and the non-trivial statement, there are not very many Z factors. There are maybe 5 or so, 5 different Z factors. So we can fix 5 numbers in order to cancel infinitely many divergences, because there are infinitely many loop diagrams which could in principle have divergences. And therefore it is non-trivial to say that by just adjusting those 5 or 4 Z factors, we can cancel all the infinitely many divergences from all the loop diagrams. So in particular, there is a very specific structure in our counter term Lagrangian with these renormalization constants. Delta Zi, which are to be chosen to cancel the divergences. And to illustrate this very specific structure, let us look at an example and derive not a full counter term Lagrangian, but derive just an excerpt of the full counter term Lagrangian, namely the gluon-gluon term in the counter term Lagrangian. So I didn't put it on the exercise sheet, but you are welcome to calculate the full counter term Lagrangian. That would be an excellent exercise if you want to see how such counter term Feynman rules look like and how they emerge. And let us look at this single example here. So we need now to plug in this renormalization transformation and really start from the classical Lagrangian, obtain the bare Lagrangian, and split the bare Lagrangian into the classical Lagrangian plus a counter term Lagrangian and read off what the counter term Lagrangian is. But we only want to do it for terms involving AA. Therefore, what is only required is we start with the AA part of the classical Lagrangian. So let's start with the AA part of the classical Lagrangian. So the AA part of the classical Lagrangian, where does it come from? From which terms? Two powers of gluon fields. Yep. Yes. How does this look like or sound like? Exactly. 1/4 FA mu nu, FA mu nu with a non-abelian field strength tensor. And then we also, let's just to be safe, let's also write down the gauge fixing term, which also contributes to the gluon. So we have xi/2 times BA plus BA times d mu a mu. That is the complete thing, and from this we only now need the bilinear part because we want the AA term. So, but the field strength tensor has also higher powers of A, third power, fourth power terms. They are now not interesting for us. But now let's do the renormalization transformation. Let's do the renormalization transformation of this thing according to that rule. What happens if we plug in the rule? If we plug in the rule and only consider here the bilinear part is this QED-like part of the field strength tensor. It contains two powers of A and some derivatives. So what happens under this renormalization with this bilinear part? So let me write it down: d mu a nu minus d nu a mu a square in quotation marks times minus 1/4. So what happens with this term under the renormalization transformation? It gets a factor of ZA. Nothing else happens. As simple as that. What happens with this whole expression? How do you know? I explained it at length, right? That was the whole point. That was the whole point. So my long explanation from 5 minutes ago was exactly to say that this doesn't change. So it doesn't change. Okay, so it doesn't change. It doesn't change. But the first term changed. And so therefore, we can now read off what the counter term Lagrangian is. I hope you see that this would be the bare Lagrangian, and the bare Lagrangian is by definition the original Lagrangian plus the counter term Lagrangian. So the counter term Lagrangian, on the other hand, is the difference between this and the original Lagrangian. So what's the difference between this and the original Lagrangian? Here there is no difference. It drops out with the counter terms. Here there is a difference, and the difference is delta ZA. So the counter term Lagrangian is really exactly this: delta ZA times minus 1/4 times this dA minus dA square in quotation marks. That's it. That is the counter term for the AA. That is exact. Let's, however, go on. How much time do we have to go on? Let's go on. To simplify it. So if we simplify this, because this will give rise to Feynman rules, to read off Feynman rules, it would be nice to simplify it a little bit. So the antisymmetric, we have antisymmetric times antisymmetric. We can cancel a factor of 2 by writing not antisymmetric times antisymmetric, but we write one term times antisymmetric. d mu a nu times d mu a nu minus d nu a mu. Okay, so that is the same. We have cancelled a factor of 2. Then we can do partial integration because the Lagrangian appears in the action where we can do partial integration, and then we can flip this derivative to the other side. We get plus delta ZA over 2 times A nu, then some differential operator times A mu AA. And what is the differential operator in brackets? We have done partial integration. This gets to here. So we have here d mu contracted is the box operator, box times g mu nu. G mu nu because I wrote A mu. Then d mu gets here, d nu acting on A mu with minus d mu. So this is our counter term Lagrangian. So how does this look like? It looks like a transverse projection operator. So we have here a transverse projection operator corresponding to gauge invariance of the Lagrangian. Since the gauge fixing did not renormalize, the only effect of renormalization comes from the gauge invariant term. So the counter term Lagrangian reflects the gauge invariance of this original F nu term. Therefore we have here a transverse differential operator. Let's write down the Feynman rule for this. The counter term Feynman rule. What is the counter term Feynman rule for this excerpt of the counter term Lagrangian? We read off interaction Feynman rules in the usual way. For each field operator there is a line which connects to a vertex. So we have two gluon fields, therefore we have two gluon lines here. Counter term Feynman rules are denoted with a cross. So this is the vertex with two gluons. So let's write down what gluons we are talking about, A mu A and A nu B. And the vertex Feynman rule is the coefficient of the fields in the Lagrangian, where there is, because these are real fields, the factor 1/2 is cancelled. And we need to go from position space to momentum space. In momentum space, a derivative becomes minus I times the incoming momentum incoming into the respective field operator. So here we have A mu, the incoming momentum into A mu, let's call it P. Let's call it P. That comes into A mu, so therefore one derivative goes into minus I times P, two derivatives become minus P square. Therefore, the Feynman rule is the following, and we also should not forget about the I, which always exists in the Feynman rule. So we have I times delta ZA times the following, namely minus P square G mu nu plus P mu P nu times Kronecker delta AB for the two color indices. That is our counter term Feynman rule coming from this particular renormalization transformation of our Lagrangian. So here we have now the concrete version of how such a counter term Feynman rule looks like, and this would give us the ability to cancel divergences. If you have a Feynman diagram with two external A's, the diagram is divergent, then you would adjust the delta ZA such that the divergence is cancelled. Very nice. But now you that is our counter term Feynman rule coming from this particular renormalization transformation of our Lagrangian. So here we have now the concrete version of how such a counter term Feynman rule looks like, and this would give us the ability to cancel divergences. If you have a Feynman diagram with two external A's, the diagram is divergent, then you would adjust the delta ZA such that the divergence is cancelled. Very nice. But now you discover something which I announced here. There is a very specific structure in the counter-term Feynman rule. Namely, the counter-term Feynman rule happens to be a polynomial of second degree in the momentum, which is transverse. It is transverse. So if you contract with one additional p mu, you get 0. So you, first of all, in order for that to cancel divergences, the divergences must also have a very specific structure. First of all, the divergence of the loop diagram must be a polynomial of second degree in the momentum and not a more complicated function, for example with logarithm of p, which often appears in Feynman diagrams. And furthermore, the divergence.
هنا في كلام جميل جدا جدا. طيب تعالوا نمسك من هنا. في كتابي السابق 55 و 54 عالجت مثل هذا الموضوع اللي هو تحديدا هذا قابلتني هذه المعادلة اللي هو البوكس جي ميو نيو ناقص دي ميو دي نيو، وذكرت أن هذه المعادلة تتناسب مع ام تربيع اللي هو الكتلة تربيع. هذا في كتابي في كتب الاثنين، بما أنها تتناسب مع ام تربيع إذا المشتقة لهم فرضا لا تساوي 0، وبالتالي هذا أعطاني المجال المغناطيسي المتغير والذي يمثل الديجريز اوف فريدم والذي يتحكم في كيو سي دي. انظر إلى كلام المحاضر هنا. طبعا البوكس اللي هو دال الامبير اوبريتور يتحول لبي تربيع، وهذا يتفق مع الكتلة. أما بي ميو هي جاية من هذه المشتقة اللي هي دي ميو، هذه المشتقة دي ميو تعطينا البي ميو دي بي ميو. لكن البروفيسور ذكر كلام عجيب، ذكر أنه إذا ضربنا هذه المعادلة ببي ميو أخرى، وهذه يكافئ أننا عملنا مشتقة أخرى، ونجد أن البي ميو ترانسفيرس، إذن قيمتها يساوي 0. وأنا في كتابي ذكرت أن القيمة يجب أن لا تساوي 0 حسب اشتقاقي أنا، لا يساوي 0، وهذا يعطينا التغير في الكتلة. إذن هناك علاقة بين الترانسفيرس وبين التغير في الكتلة. يعني إذا كان هذا الترانسفيرس يعني عمودية أو مستعرضة مثل الموجة العمودية وموجة مستعرضة، وبالتالي إذا ضربنا فيها هذا الترانسفيرس اللي هو بي ميو، إذا ضربنا بي أخرى، أفرض أن بي ميو أخرى، فإنها تتكنسل أو تختصر مع البي ميو الأخرى، بي نيو. إذا عملنا ذلك ستكون بي تربيع أو بي نيو، وهذه عبارة عن مومنتوم مثلا لونجيتيودينال ومومنتوم طولي مضروب في مومنتوم مستعرض، وهذا يعطينا 0. وهو لا يتفق مع ما توصلت إليه في كتبي أنه لا يساوي 0. هذا يعني شيء غريب، أنه الترانسفيرس لا يكون ترانسفيرس خالصا إذا فرضنا أنها لا تساوي 0 وأنها تتناسب مع ام تربيع وتتناسب مع التغير في الكتلة. إذن هنا لا الحديث يكون عن هذه البروجيكشن أو هذه البروجكشن بين هذه الثلاث مومنتومز لا تساوي زيرو. وهنا هذا يعطينا شيء علينا نبحث عنه، وهي ما علاقة الترانسفيرس أو كيف يتم تحولات الترانسفيرس. ربما يكون مر علينا في السلسلة ولكن أنا لم أضع بالي له. يعني الترانسفيرس يمكن أن يكون ليس ترانسفيرس خالصا، وإنما يمكن أن يكون مائلا أكثر إلى زوايا معينة. إذا أصبح ذلك يمكن حساب التغير في الكتلة من خلال هذه الزوايا، قياس هذه الزوايا. فهذه معلومة جد جميلة وجد خطيرة، ولو كنت أعلمها كنت أضفتها في كتابي، لكن هذه ما لم أكن أعلمها، لأنه لم أكن أعلم أني سأجرى هذا الاشتقاق بالنسبة للأميو وأحول هذا الاشتقاق إلى، أو بالنسبة للإف ميو وأحول هذا الاشتقاق إلى مومنتومز، ثم بعد ذلك أجري هذه الايدنتيتي. هذه ايدنتيتي طبعا مرت علينا كثيرا، خصوصا في السميشن للبولاريزيشنز أو السميشن للبولاريزيشنز يعطينا هذا الايدنتيتي بالمناسبة. والسميشن للبولاريزيشنز في حالة الونتو تعتبر بولاريزيشنز، تعتبر ترانسفيرس، بالتالي مفترض أن تعطينا زيرو على ما أظن ذلك. وبالنسبة لللونجيتودينال اللي هو الاس والال على ربما لا تعطينا زيرو، وهذا ما يؤكد كلامي. لكن هذه الايدنتيتي فيها شيء كذا أنا لا أعلمه حتى الآن، فهذا يجعلني ربما أعيد مشاهدة الفيديو الكوانتيزيشن اوف سبين 1 بارتكلز، لأنه الكوانتيزيشن اوف سبين 1 بارتكلز فيه هذه المعلومة، معلومة في غاية الأهمية، معلومة في غاية الأهمية. فالضرب في ثلاثة مومنتومز مفترض أن يعطوا زيرو. إذا أعطى زيرو هذا يعني التغير في الكتلة اللي هو بي مومنتوم أخرى مضروبة في بي تربيع. بي تربيع عبارة عن الكتلة، فالتغير في الكتلة يساوي زيرو. وهذا ما تذكره تيار نيثر، هذا ما تذكره سيمتري في نظرية نيثر. التغير في الكتلة يكون زيرو، وبالتالي يعطينا التغير في تيار نيثر يساوي زيرو. أنا افترضت لا، حسب نظريتي افترضت لا أن التغير في تيار نيثر لا يعطينا زيرو. بما أن التغير في تيار نيثر لا يعطينا زيرو، يعني بارشال جي ميو لا يساوي زيرو، هذا يعطينا أن هناك شيء ما يتغير في التيار. ما هو الذي يتغير؟ الكتل، السيمتري في الكتل. يعني الكتل ليس فيها سيمتري، بالتالي تخرج هذه الكتل واحدة كبيرة واحدة صغيرة، وكتل متنوعة ليست كتل واحدة. يعني الفيلد الواحد بالنسبة للفيلد مثلا الكترونيك فيلد، هذا في التفاعلات العميقة جدا لن يعطينا كتل تتناسب أو كتل تعبر عن كتل الإلكترون، وإنما تعطينا كتل أكبر من الإلكترون، مثل كتل كواركس. الإلكترونات مش مثل كتل الميون أكبر من الإلكترون. أنا لو كان أقصد الكتلة لا أقصد كمية التحرك، لأنه كمية التحرك تعطينا طاقة إضافية أو كتلة إضافية للإلكترون، لكن أقصد التيار الذي يتعلق بكتلة الإلكترون فقط، لأنه الإلكترونيك فيلد يعطينا كتلة الإلكترون لا يعطينا كتلة الميون، فالإلكترونيك فيلد يعطينا كتلة الإلكترون، والميونيك فيلد يعطينا كتلة الميون. لكن انظر إلى هذا، إذا كانت ضرب بي أخرى أو مومنتوم أخرى لهذه الترانسفيرس بي ميو بي نيو لا يعطينا زيرو، فهذا مباشرة يعطينا الاختلاف في الكتل، وهذا يعطينا أنه تخرج كتل مختلفة من الانتراكشنز بين الالكترونيك فيلد، وهذا في الواقع موجود في المصادم في المصادم الجزيئات الضخم. نجد أن هناك جسيمات أكبر كتلة من الإلكترون تخرج من التفاعل، لكن لا تمكث كثيرا. يعني مثلا عندنا الميون يتحلل في 10 سناقل 6، عندنا التاو يتحلل في أقل من ذلك. كلها عبارة عن السكند جنريشن والثيرد جنريشن تخرج من داخل تفاعلات الإلكترونات، وهذا ما يؤكد أن نظريتي صحيحة. لكن هناك مدلول عميق جدا سأحاول أن أكتشفه في هذه الضرب الثلاثي بين البي في بي ميو في بي نيو. هناك مدلول عميق جدا جدا بحسب الوارد ايدنتيتي يعطينا زيرو. بالمناسبة هذه تعتبر وارد ايدنتيتي، الوارد ايدنتيتي تقول يعطينا زيرو، وأنا قلت لا يعطينا زيرو. إذن الوارد ايدنتيتي يدخل في هذا الأمر أيضا، الوارد ايدنتيتي يدخل في هذا الأمر أيضا. هذه معلومة في غاية الأهمية، ويؤكد صحة كتابي طبعا، يؤكد صحة كتبي. وما ذهبت إليه أن إذا نظرنا إلى سيمتري آخر غير السيمتري الخاص بالفضاء، السيمتري الآخر ليس لديه مكان إلا الكتلة، وبالتالي الخمسة أبعاد لكلوزة اللي هي معادلة كلوزة أو نظرية كلوزة، إنه هناك 5 أبعاد للجاذبية. الخمسة أبعاد لكلوزة هي 4 أبعاد تتعلق بالفضاء، والخامس تتعلق بالكتلة. وربما كلوزة أينشتاين لم يصل لهذا، أن الخامس يتعلق بالكتلة. وأينشتاين كان يعرف النيزر من بدري جدا، ويعرف أن السيمتري للنيزر يجب أن يكون متساويا. وأينشتاين يؤمن بالسيمتري بالمناسبة، لأن النسبية الخاصة تعتمد على السيمتري اللي هو لورنس انفاريانس. فهذا السيمتري أينشتاين لا يستطيع أن يتخطاه، وإلا النسبية الخاصة كانت خاطئة. فهو يؤمن بهذا السيمتري، وبالتالي ربما يكون توقف عند هذا الحد اللي هو الحد الذي يقول أن 3 مشتقات للإف ميو أو للإي ميو أو للإف ميو نيو، 3 اشتقاقات يجب أن تساوي 0. فبالتالي آخر حد وقفوا إليه أينشتاين وكلوزة وأن يعطينا هذا الاشتقاق، يعطينا معادلات ماكسويل، أو قبل معادلات ماكسويل يعطينا البوتنشالز اللي هو الA، وقفوا في أظنه في الA والفاي، هذه بوتنشالز، أو ربما وقفوا في معادلات ماكسويل. يجب أن نتأكد من هذه المعلومة المهمة جدا جدا. إذا وقفوا في معادلات ماكسويل لا يستطيعون أن يعبروا من معادلات ماكسويل إلى الجاذبية والتي تتحكم في الكتل. الجاذبية تتحكم في الكتل أو ناتجة عن طريق الكتل. فمعادلات ماكسويل تعتبر لينير، الديفرنشيال أو الديريفيتيفز تكون لينير، بالتالي ليس هناك ديريفيتيف سكوير. ونظرية تقول أن هناك ديريفيتيف سكوير إذا أردنا أن نتحكم في الكتل. فنظرية أينشتاين وكلوزة أو نظرية ماكسويل تقول أن الديريفيتيفز بالنسبة للمجال الكهربائي والمجال المغناطيسي يجب أن تكون لينير. طيب ماذا إذا عملنا أجرينا ديريفيتيف أخرى للمجال الكهربائي؟ يعطينا 0، اللي هي معادلة الموجة المعروفة. معادلة الموجة اللي هو نابلا سكوير أو بارشل على بارشل تي سكوير ناقص نابلا سكوير للإي يساوي 0. هذه معادلة الموجة، وتعطينا موجة مستقرة بالمناسبة. تعطينا موجة منتشرة مستقرة، وهذا ما يحدث في التيار يحدث في الفوتون يأتينا من الشمس وهو مستقر تماما. طبعا في تايم دايليشن، في دوبلر شيفت بالمناسبة ناتج من الجاذبية. لماذا حدث هذا الدوبلر شيفت؟ هذا أيضا سؤال نسأله. لماذا حدث الدوبلر شيفت؟ حدث لأنه الجاذبية تعمل على كسر هذا السيمتري، اللينير ديبندنس، تعمل على الكسر. الجاذبية لديها خاصية أخرى، أن معادلات ماكسويل قد تكون نون لينير أو قد تكون معادلات بالدرجة الثانية، وهذا يعطينا اختلاف في الكتل. أينشتاين وكلوزا لم يصل إلى هذه المرحلة بالمناسبة، لم يصل إلى هذه المرحلة، ووقفوا عند ماكسويل، ولم يستطيعوا أن يحسبوا الكتل من معادلات ماكسويل، لأنه لا يمكن أن يكسروا هذا السيمتري. معادلات ماكسويل عميقة لدرجة أن أينشتاين كان يعتقد فيها اعتقادا كاملا، وأنها بسببها يعني دمر فرضية نيوتن الفيزياء الكلاسيكية أن الزمن مطلق وأن المكان مطلق بسبب معادلات ماكسويل هذه. فأينشتاين لم يستطيع أن يعبر خلافها. هذا كلام والله يستحق أن أعمل فيديو خاص به. أينشتاين لم يستطيع أن يعبر منها، فتوقف عند هذا الحد، وبالتالي أصبحت الخمس أبعاد لكالوتسا التي تضم الجاذبية وكهرومغناطيسية لا تستطيع أن تذهب أكثر من ذلك لتعطينا الكتل أو تتنبأ بمصير الكتل، لأن الجاذبية لا يعطينا الكتل، التغير في الجاذبية تعطينا الكتل. يعني إذا هناك مشتقة أخرى للجاذبية حتى تعطينا الكتل، لكن الجاذبية ذاتها لا يعطينا الكتل، لأن الجاذبية عبارة عن قانون ثابت بين الكتل. يعني مثلا التجاذب بين القمر والأرض ثابتة، طبعا هي تتعلق بالمسافة تربيع، فإذا هناك تغير من الدرجة الثانية في جاذبية، يعني ليس ثابتة. لكن ماذا يحدث إذا غيرناها لتغير الدرجة الثالثة؟ طبعا لا يمكن أن نعتبر R تكعيب، لأن R تكعيب سيهدم قانون نيوتن، وبالتالي من الدرجة الثالثة سيعطينا دلتا M أو دي M على دي R تربيع، والدي M على دي R تربيع المفترض تعطينا ما هي معادلة من الدرجة الثانية. لكن إذا عملنا M ذاتها تتغير، بالتالي يمكن أن نعمل معادلة من الدرجة الثالثة اللي هو دي M دي تكعيب M على دي R تكعيب. هذه معادلة من الدرجة الثالثة تحافظ على قانون نيوتن، لأن قانون نيوتن كوني، تحافظ على قانون نيوتن، لكن تخبرنا بالشيء في غاية الأهمية أن هذه المعادلة تتحكم في الكتل. إذا أردنا أن نجعل، يعني إذا حاولنا أن نحسب التغير أو هذه المعادلة من الدرجة الثالثة، فإن قوة نيوتن وقوة كولوم طبعا أيضا، قوة نيوتن وقوة كولوم، التغير في قوة نيوتن وقوة كولوم تعطينا التغير في هذه الكتل، حيث هذه الكتل يمكن أن تتضخم وتصغر بالنسبة لR تكعيب. يعني هذه المعادلة التي فيها R تكعيب هذه تؤثر داخل الكتل ذات نفسها وداخل الشحنات ذات نفسها، R تكعيب، وبالتالي ستكون R تكعيب عبارة عن R تربيع وهي المسافة بين الكتل مضروبة في R أخرى وهي تمثل الفرق بين هذه الكتل. يعني مثلا كتلة الشمس وكتلة القمر، كتلة الشمس 10⁻²24، كتلة القمر 10⁻23، وهي تتناسب بقانون نيوتن بقانون التربيع العكسي R تربيع. إذا فرضنا أن حاولنا أن نفاضل قانون نيوتن بالنسبة لآر أخرى، وبالتالي نحسب بارشل اف على بارشل ار. ماذا تسمى ار هذه؟ ار هذه تسمى ار كتلية، حيث أنها تعطينا الفرق بين 10 سي 24 إلى 10 سي 23. وبالتالي هذه الار تعطينا إذا تغيرت كتلة الأرض من 10 أس 24 إذا 10 أس إلى 10 أس 26 أو إلى 10 أس 30، ونريد أن تظل القوة ثابتة، هذا يعني كيف تتغير الكتلة M للقمر. وطبعا هذا معروف تعويض في قانون نيوتن مباشرة، لكن نحن نريدها كمشتقة مشتقة تعطينا continuous variations. فالآر الثالثة هذه هي مباشرة تربطنا بمدى التناسب بين التغير بين الكتلة وبين كتلة الأرض وبين القمر. هذا الأمر تعتبر ثابتة لأن كتلة الأرض ثابتة وكتلة القمر ثابتة. أما في التفاعلات دون ذرية وفي الثقب الأسود الكتلة غير ثابتة. الثقب الأسود يأكل كتل كل حين وحين، وبالتالي الجاذبية له تتغير. التفاعلات دون الذرية تتغير بموقع الكوليجن أو التصادم بالنسبة للكيرفيتشر اللي هو بالنسبة الكروس سكشن للتفاعل، أو بالنسبة إلى وسط التفاعل، هل الكوليجن هذا حصل في العمق في التفاعل أو في الطرف، وبالتالي هذا يؤثر على التغير في الكتل ويكسر السيمتري لهذا الكتل. يكسر السيمتري أولا لقانون نيوتن، يكسر السيمتري لقانون كولوم، ويكسر سيمتري آخر النسبية الخاصة، ويكسر سيمتري ثالث الرابع معادلات ماكسويل، ويكسر سيمتري خامس تيار نيزر اللي هو سيمتري في تيار نيزر. إذا نظرية تستطيع كسر كل هذه السيمتريز من خلال هذه المعادلة فقط. هذا فيديو ربما أسجله في أو أكرره في فيديو آخر، أو ربما أقطع هذا الفيديو وأعمله كفيديو آخر قائم بذاته يتعلق بهذا الفيديو الذي أسجله، لأنه هذه في معلومة في غاية الأهمية، وهذه فرضية يمكن دحضها، يعني يمكن أن نثبت خطأها، وبالتالي تهدم نظريته كلها أو الفرضيات الأخيرة اللي هو كتاب 54 و 55 وربما كتاب 53 أيضا، كلها تهدم بفعل هذه إذا وجدنا طريقة لضغط هذه النظرية. طيب هذا التسجيل هذا أنا في كم ساعة أو 47. جميل. طيب تعال نواصل.
Must be transverse. If you hit the self-energy with p mu, you must get 0. Otherwise, you cannot cancel the divergence with this counter-confining rule. If, however, magically maybe the divergence has this form, then it could be possible to cancel it by just adjusting the numbers at a. And that is the case. Why is that the case? Because of some Slavnov-Taylor identity which guarantees the divergence to be transverse. And also because of the fundamental theorem of renormalization, namely that divergences at the next order are always polynomial.
طبعا ممكن نرجع لهذه الجزئية التي ذكرها المحاضر بالذات، يمكن نرجع إلى هذه الجزئية. لماذا الرينورماليزيشن يعطينا 0؟ لأنه أصلا الرينورماليزيشن يعني بهذه الآلية الترانسفيرس وضربها في البيئة الأخرى التي تعطينا 0 في هذه المعادلة، وهذا يعطي رينورماليزيشن 0 أو ريجولاريزيشن. لأنه أصلا في نظرية الريجولاريزيشن نحن ثبتنا أن التغير في الأبعاد التي هو يتعلق بالتغير في الكتل، فوجدنا أنه التغير في الأبعاد صغيرة جدا، وبالتالي الريجولاريزيشن يعطينا ثابت، يعني كأنما الفضاء ثابت، كأنما الكتلة ثابتة. بما أن الكتلة ثابتة إذا الدلتا ام تكون يساوي زيرو، وهذا ما يعطينا لا 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 هذه الايدنتيتي التي ذكرها، وهذا المعادلة تكون صحيحة. يعني أيضا أتفق مع نظريتي مع ما ذهبت إليه في الشرح قبل قليل.
In the momentum and not something else. That is the general theorem of renormalization. So, but the general story at this point, since we are not yet at the proof of renormalizability, but we are just at collecting building blocks, okay? At this point we have collected a building block, namely we have collected the renormalization transformation giving us a certain counter term structure, and the outcome of this is that this is transverse, and therefore only ultraviolet divergences of this particular form can be cancelled. So that is the result of this section. All right, so how much more time do we have? Actually, it seems we were incredibly slow. So should we do another section? I see a lot of fear in some eyes. Let's try to do another section. Yep. That is of course an excellent question, and it does not, since we assume that these z factors are of the form 1 plus delta z, and the delta z is of higher order by definition. So we choose it to be of higher order, and therefore at the lowest order in the coupling constant, the lowest order in perturbation theory is completely unchanged, and the only changes appear at higher orders in perturbation theory. And then we will always choose the delta z in such a way that they are zero at lowest order and are non-zero at higher orders, and then they will be adjusted in a way which must be compatible with all the structures that we want to guarantee, for example unitarity of the physical S matrix, finiteness, and so on. And that is in fact the discussion that we are leading. But what we already know about leading order tree-level Feynman diagrams remains correct forever, because that is not changed. So let us just do a small additional section, BRST renormalization. Because that is just transferring the renormalization transformation onto the level of the BRST transformations, and it is also a little bit an answer to your question, because at tree level and so far we looked at BRST invariance of the Lagrangian. So one question could also be, does the Lagrangian remain BRS invariant? And it does not, but it remains invariant under a renormalized BRS transformation. And so let us write this down. So the definition is we can introduce a simple S pair. So far we had S for BRS transformations of all the fields, and we now introduce S pair such that the following simple relationship holds, namely if S pair acts on a bare field, then you get the same as the original S on the original fields, but on the result you apply the renormalization transformation. Okay. So that simply means that S pair acts on the bare stuff just like the usual S, but replacing everything with bare quantities. Very simple. So for example, the bare BRS transformation of a bare quark field would be, for instance, the following. Minus I gauge coupling times ghost times quark, that is the original transformation, and now we simply write bare gauge coupling times bare ghost times bare quark field. And then we have defined the operation S bare on all the fields. And then we define also something a little bit trickier, which is however kind of the same, as renormalized on a renormalized field phi. That is defined in the same way as the bare S, but it looks different. It is defined as 1 over square root of Z phi times the bare BRS transformation of the corresponding bare field. So in a way, this simply means that S renormalized acting on square root of Z phi times phi is the bare BRS transformation on the bare field. So really this is the bare field. So you could say S renormalized is the same as S bare, but we use it differently. We use S renormalized to act on renormalized fields, and we pull out these field renormalization factors. But it acts in the equivalent way. But you see that both S bare and also S renormalized, they do the same thing, but they do not do the same as the original S. There is a change because, for example, here, let's say, for example, what happens for the quark field? S renormalized acting on the quark field. What do we get? What do we get literally from this definition for the quark field? We need to divide that by the Z factor of the quark field, and then we obtain minus I times the bare gauge coupling times the bare ghost times the renormalized quark field. Okay? So then you see that S renormalized on a quark field acts like this. Here you have something bare, but the original S on the same quark field would have here the gauge coupling without bare and the ghost without bare. Therefore the original S doesn't do the same as the renormalized or bare BRS transformation. So we have changed it. And now let us write down some obvious facts. Clearly, our original Lagrangian was BRST invariant. The original S acting on the original S classical is 0. Now if we apply a renormalization transformation to absolutely everything in this equation, then it remains 0, because we just put a label bare onto all quantities. So then the same cancellation which happens before happens also afterwards. Therefore totally obvious, S bare defined in that way, acting on the bare Lagrangian, gives also 0. But now we have this S renormalized, which is the same as S bare, but which acts on the original fields. It's a tautology basically, but we can write down S renormalized acting on L bare equals 0, because it's the same thing. And that can also be written like this: S renormalized acting on the classical action plus the counter term, Lagrangian, sorry, gives also 0. And then indeed you see that our BRST invariance has changed by the renormalization transformation. This bare action is not invariant under the same BRS transformation as the original one, but under a modified one. And that might be important. Anyway, it is true, and we can take it into account. But because of your question, we already know that the Z factors are 1 plus higher orders. Therefore, at lowest order, again, there is no change whatsoever. But there are changes in this which are relevant at higher orders. So, but anyway, this whole list of equations, all of these equations are valid. So we have a statement of the symmetry of the original action, a statement of the symmetry of the bare action after renormalization, and so on. So we have BRS invariance with different transformation laws, but we have BRS invariants of both the original and the renormalized theory. And as you already guessed, the important Slavnov-Taylor identities are of course a consequence of BRST invariance. Since we need the Slavnov-Taylor identities at higher orders, it is important to know what is the BRST invariance at higher orders. And now we know it. Okay, I think time is up, and therefore we can close here. And just to summarize once again, in the morning and in the beginning of today's afternoon, we have discussed a lot about the physical implication of our BRST formulation of Yang-Mills theories. There are unphysical degrees of freedom in our theory, which is a necessity if we want a local and Lorentz invariant description of physics. But the unphysical parts and the unphysical elements are under control with Ward identities and Slavnov-Taylor identities, and they have implications like terms dropping out in the Lorentz transformations, gauge fixing parameter dropping out of matrix elements, and this cancellation of unphysical degrees of freedom in the unitarity discussion of the physical S matrix. So all of this gives us confidence in the interpretation of the theory. Now we discuss renormalization. We already also discovered that symmetries and Slavnov-Taylor identities will be important in order to see that, for example, divergences are transverse and can be cancelled by field renormalization of the gluon field, and so on. And in the next lecture, we will put everything together and at least sketch the logical flow of all the proofs, where we will then give the answers to the basic questions that the theories will be finite in this way, and unitarity and Lorentz invariance and gauge independence will also remain valid at all orders. Okay, so see you next week.